Our today's topic for discussion is beta-lactamases and the beta-lactamase inhibitors. Beta-lactamases are a family of the enzymes which are produced by many gram-positive and gram-negative bacteria that inactivates the beta-lactam antibiotics by hydrolyzing the beta-lactam amide and hence opening of the beta-lactam ring. So this is the beta-lactam amide. So this is the site of action of the beta-lactamase enzyme for the opening of the beta-lactam ring. The opening of the beta-lactam ring in penicillins, for example, results in the formation of the penicilloic acid, which is an inactive product. So let us now understand that how these beta-lactamase work. This is the penicillin having a beta-lactam ring in their structure, and this is the serine residue in the active site of the beta-lactamase enzyme having OH group in the structure. The general base B1 activates the serine for the nucleophilic attack on the amide carbonyl carbon, that is the carbon number 7, generating covalent acyl enzyme. This is the covalent acyl enzyme and this is the acyl group via the tetrahedral oxyanionic acylation transition state. This is the tetrahedral oxyanionic acylation transition state. Now the general base B2 activates the incoming deacylating water molecule DW for the nucleophilic attack on the acyl enzyme carbonyl. This is the acyl enzyme carbonyl, liberating the penicilloate product. This is the penicilloate product via the tetrahedral deacylation transition state. This is the tetrahedral deacylation transition state. So the strategies for combating this form of resistance have included the development of new beta-lactam antibiotics that are more resistant to the cleavage and the development of the class of the enzyme inhibitors called as beta-lactamase inhibitors. Although beta-lactamase inhibitors have little antibiotic activity of their own, but they expand a useful spectrum of beta-lactam antibiotics like penicillins and the cephalosporins by inhibiting the beta-lactamase enzymes which are produced by the bacteria itself to deactivate them. Now coming to the classification based on their structure. There are two types of the beta-lactamase inhibitors depending upon their structure. The first one is those drugs which itself have a beta-lactam ring in their structure. For example, the clavulanic acid, the sulbactam and the tazobactam, and all of them have a beta-lactam ring in their structure. They are also referred as the suicidal beta-lactamase inhibitors because they cause irreversible inhibition of the enzyme by producing a metabolite. Another class of the drugs is those that do not contain a beta-lactam ring in their structure. For example, the avibactam, the relibactam and the vaborbactam. All of them act by the acylation of the active site of the enzyme to inhibit the enzymatic activity. Now, what are the essential requirements for the beta-lactamase inhibition? The first is the strained beta-lactam ring. It is for the inhibitors which contain the beta-lactam core in their structure. The second is the enol ether. The enol ether is an alkene with an alkoxy substituent. So this is the alkene with the alkoxy substituent. This is the double bond and the R which is directly attached to the oxygen. This side chain is very much important because they produce the intermediates which are irreversibly bind to the enzyme. The double bond of the enol ether has a Z configuration. There is no substitution at C6 position. That is, there is no acyl amino side chain at 6th position. The stereochemistry at 2nd and 5th position is R stereochemistry. At 2nd and 5th position is R stereochemistry, and also there is the presence of a carboxylic acid group in the structure. So these are the essential requirements for the beta-lactamase inhibition. Now let us understand that how beta-lactamase inhibitors act on the enzyme to inhibit its action. So this is the drug, that is the clavulanic acid, having a beta-lactam ring in the structure. So it has some affinity for the beta-lactamase enzyme, and this is the enzymatic serine residue having OH group, and the OH group interact with the amide present in the beta-lactam ring, which produce the hydrolysis of the ring to open the ring, and this results in the production of the metabolite 1. This metabolite is attached to the active site of the enzyme at the serine residue, but this metabolite further undergo cleavage to produce the another metabolite, that is the metabolite 2, and this metabolite 2 produces irreversible inhibition by cleaving the oxazole ring. In this ring, this enol is converted to the ketone, and this amine is converted to imine. The metabolite 2 is very important because it has a positive charge on nitrogen. So they need some negative charge nucleophile for the strong interaction, which are already available with the enzyme. So both of them make a strong interaction to inhibit the enzyme irreversibly, and this is the reason why these drugs are known as the suicidal inhibitors. Now coming to the combinations which are available, the first and common combination is clavulanic acid combined with the ampicillin, which is also known as amoxiclav. The second is the sulbactam combined with the ampicillin, tazobactam combined with the piperacillin, avibactam combined with the ceftazidime, relebactam combined with the imipenem, and the vaborbactam combined with the meropenem. All of these combinations are used for combating this form of the resistance and have included in the development of new beta-lactam antibiotics.